Energy Basics, Matter and Energy. You should be really good at identifying the forms of energy taught to intermediate students. Now let's look at the definition of energy. We'll start with the question, what is energy? And review the answers given in the primary, elementary, intermediate, and the secondary grades by need.org. What is energy? This is the answer given for primary students in grades PK through 2. Energy makes change. Light makes change. Light is energy. These are more answers to that question, what is energy, for primary students. Heat makes change. Heat is energy. Motion is change. Motion is energy. These are the last answers to the question, what is energy? Sound is change. Sound is energy. Growth is change. Energy makes things grow. You have probably learned that the definition of energy is the ability to do work. That explanation wouldn't mean much to a 5 or 6-year-old student, so NEED has provided some great visuals to help capture the many different facets of energy. Which one of these was missing from our list of the 9 energy forms? In the primary grades, energy is related to life and growth. At the intermediate level, where forms of energy are introduced, life and growth are not specifically included. Indirectly, we see the results of plants and animals' lives by the chemical energy they store in their bonds. We've seen how energy is described for the primary grades. Let's move on to the elementary students in grades 3 through 5. Note that they have kept the connection between energy and living things and introduced electrical energy. We see information about the conservation of energy for the first time. Let's take a closer look at the language used for energy conservation. Energy doesn't disappear. There is the same amount of energy today as there was when the world began. When we use energy, we don't use it up completely. We change it into other forms of energy. When we burn wood, we change its energy into heat and light. When we drive a car, we change the energy in the gasoline into heat and motion. There will always be the same amount of energy in the world, but more and more of it will be changed into heat. Most of that heat will go into the air. It will still be there, but it will be hard to use. Do you agree with these statements? Now let's look at the description of energy for intermediate students in grades 6 through 8. These are the 9 forms of energy you used for the forms of energy activity. There is less information about the connection between energy and living plants and animals in the intermediate grades. Let's take a closer look at conservation of energy for intermediate students. For reference, I've copied the elementary information. At this level, students have learned about scientific laws and theories, so this concept is now called the law of conservation of energy. Energy is neither created nor destroyed is probably the way you memorize this law. This law is accepted as dogma by most scientists. That means it is a core assumption, accepted without question. Before we investigate the source of this law, let's finish our review of energy at the secondary level. This is how NEED teaches energy to secondary students in grades 9 through 12. Notice the same 9 forms of energy we used before. I'll enlarge parts of these pages so you can read the fine print. In the column on the left, we see a definition of energy, and the reference to growth is back. Also note the exception to the law of conservation of energy on the right. Energy can change form, but the total quantity of energy in the universe remains the same. The only exception to this law is when a small amount of matter is converted into energy during nuclear fusion and fission. Let's review the definitions of energy and the conservation of energy. On this slide, I've copied the definitions of energy provided by NEED at each educational level. At the primary level, the definition is stated in terms that young children will understand. In elementary grades, students learn about work, so that concept is introduced. At the intermediate level, the definition drops the change component, but it is back again at the secondary level. The classic definition of energy as the ability to do work came from physicists. By adding the ability to produce change, we make the definition more understandable by young children. I propose adding a third component, the ability to sustain life. This makes our definition more complete and recognizes the importance of energy for all living things. What do you think? Are you comfortable with this new working definition, or do you prefer to stick with the classic definition? For your assignment, you'll comment on this issue. Now let's look at the law of conservation of energy. Remember that it is energy cannot be created or destroyed. The law of conservation of matter is very similar. Matter cannot be created or destroyed. The law dealing with energy, the conservation of energy, is also known as the first law of thermodynamics. It includes the heat, work, and internal energy of systems. Internal energy refers to the motion of atoms or molecules. This does not include energy inside the atom, primarily because this was developed in the mid-1800s, before we had a good conception of the atom. Let's take a quick look at the history of this law. Before the 1800s, people did not understand that light, heat, sound, electricity, and motion were all different forms of energy. James Joule showed that work energy and heat energy are interchangeable and conserved. Joule used a falling weight that moved a paddle wheel in a liquid. The turning paddle wheel warmed the liquid. The increase in heat was equal to the loss of potential energy by the falling weight. Isaac Newton used Joule's work to create a mathematical expression of the first law. And James Watt used this concept to calculate the efficiency of steam engines. I've highlighted these names because you'll see them later as units of energy, work, and power. The conservation of energy was very important when James Watt was calculating the efficiency of steam engines. He was comparing the energy put into the engines with the energy output. There could not be any energy created or destroyed, or it would ruin his calculations. To understand this, let's consider an example you could use with your students. You want to find the amount of money you make by doing odd jobs for a year. Every time you are paid for raking a yard or shoveling snow, you put the money in a piggy bank. At the end of the year, you will open the bank and count your money. This sounds simple, but what if money is created when your dad puts his extra pocket change in your bank? What if your little brother borrows some of the money but doesn't return it? This is like money being destroyed. In order to calculate your earnings, money cannot be created or destroyed. The same thing was true for James Watt. He counted all the energy in and all the energy out. He had to assume that energy could not be created or destroyed in his system. The law of the conservation of energy worked great. It allowed calculations of efficiency and enabled scientists to compare many different forms of energy. Then, in 1905, a new scientist with new ideas published his works. In 1905, this is the way women dressed and what some of the cars looked like. But do you recognize this famous scientist? This is how Albert Einstein looked in 1905. This was a big year for him. In June, he published a paper on photoelectricity. In September, he published a paper that introduced the idea that matter could be transformed into energy and vice versa. His ideas were very radical at the time, and there was little evidence to support them. It wasn't until 1921 that he would receive the Nobel Prize in Physics for his work on the photoelectric effect. The atomic bomb was developed based on his famous equation E equals mc squared, and it illustrated nuclear fission. But there were other very common examples of nuclear energy. Our sun is an example of nuclear energy. On the sun, hydrogen atoms join together to form helium. The mass before is greater than the mass after the combination. Was the matter destroyed? No, it was transformed into energy. This transformation also takes place on every star. Do you think the total quantity of energy in the universe remains the same? What about the total quantity of matter? In an atomic bomb, uranium atoms are broken into krypton and barium and neutrons. The mass afterwards is less than the mass before. Was the matter destroyed? No, it was transformed into energy. Nuclear fission and fusion are examples of the exception to the law of conservation of energy and of the law of conservation of matter. Instead of stating these as separate laws, which worked fine before 1905, is it time to update our laws to reflect new theories and evidence? What if we combine the two laws into one? Our new law would be energy and matter cannot be created nor destroyed, but they can be transformed. Energy can be changed into matter, and matter can be changed into energy. The total quantity of matter and energy in the universe remains the same. What do you think about this way of teaching energy? Please think about it and post your comments. This concludes our lesson. You have a lot to think about. Please share your thoughts about using a new working definition of energy and changing the laws of conservation of energy and matter on our discussion area. I'm looking forward to reading your comments. Oh, and if you have started reading Switch, also comment on how the rider, elephant, and/or the path relate to changing how we teach about energy.